Can I start the class? Yeah, okay, thank you. Yeah, very good morning to all. Okay, that is in the last session, what we have been seeing is that deadlocks in process management, in operating system, process management is very one of the important components. Okay, in that we haven't already covered what is process, what is process scheduling algorithms, and process synchronization techniques for time, and we're also seeing about and deadlock with different resource type. And after that, we have been saying that how the system has been internally implemented, in the sense the system is implemented by using three system calls. So number one, request, use, and release. That implies before executing any particular process, first of all, you have to make a requisition to the operating system. I want these particular resources. That can be done by using request system call. And once the resources has been sanctioned, you are allowed to continue the execution. That can be done by using use system call. Once the execution has been successfully completed, you can release that particular resources to back to operating system by using release system call. This is what you have done. Now, coming to the next very important topic of discussion we have been done in the last class is that so the deadlock characterization, or you may call it as the necessary conditions which is causing for a deadlock. The necessary conditions which is causing for a deadlock is that number one, mutual exclusion, number two, hold and wait, number three, no preemption, number four, circular wait. The beauty in this is that in order to enter the system into deadlock state, any one of the condition is sufficient. After coming, after deadlock is encountered, if you observe it, all the four conditions are going to be simultaneously hold. That's it. Now, how do you explain deadlock characterization? The deadlock characterization has been already demonstrated by using a resource allocation graph technique. You know what is a graph? A graph is an ordered pair of vertices and edges. The vertices are represented with the processes and resources. And there are two types of edges that is used to construct your resource allocation graph. Number one is requesting. Number two is going to be called as requesting edge. Number two is assignment edge. In this PI to RJ, that implies process PI is requesting for a resource RJ, and assignment edge sense the resource RJ is already assigned to process PI. So already we have been saying this is a resource allocation graphs. Already we have been seeing in the last class. That is, in case if your computer system is having single instance of each and every resource type, then the deadlock indicates that there is a cycle in the system. Cycle indicates that the deadlock in the system. That's it. But whereas in the case of a multiple instance of each resource type, then a cycle does not lead to a deadlock, but deadlock is compulsorily holds a cycle. Now, and the next what we have been seeing is that what are the different methods which can be used for handling deadlocks. So in order to handle deadlocks, there are three kinds of solutions we have. Number one, we can use a protocol to ensure that the system will never enter into the deadlock state. Number two, we can allow the system to enter a deadlock state, and using an algorithm, you are finding whether the system is in deadlock state or not. And after that, use another algorithm to break the deadlock, that is recovering from the deadlock. And the third very important one is we can ignore the problem altogether and pretend it that the deadlocks never occur in a system. This is generally what we are going to be followed in Unix operating system. Now, coming to the next one, deadlock prevention. So first one. So what is deadlock prevention in the sense? So what are the necessary conditions that is required to encounter a deadlock? What are the necessary conditions for encountering a deadlock? Please try to see that such conditions should not be held. So this is not possible. Already we have been seeing in the last class. And coming to the next very important one is that deadlock avoidance. Okay, what is deadlock avoidance? You need to define a safe sequence in such a way that the system will never enter into the deadlock state. So the resources must be allocated in such a way that the currently available resources must be satisfied any one of the waiting process. The currently available resources must be satisfied any one of the waiting process. This is recursively satisfied until the whole jobs has been completed from the ready queue. Already we haven't defined safe sequence and we haven't demonstrated with a problem. Okay, a computer system with having 12 resources and 3 processors running. What is the maximum needs of each and every process? What is the currently holding? And new requested resources has been allocated. And by allocating such kind of a new resources to a process, please try to see that the system must be always lives in safe state. If you are not properly defining a proper state sequence, then it is not possible. Already I told you this example. Now this is what we have been seeing in the last class. Now we are going to be moving to the next very important topic is Banker's algorithm. Okay, what is this Banker's algorithm? Okay, now already we have been seeing that in case if a single instance of each resource type, if a single instance of each resource type is available, so simply you can use the resource allocation graph. By using the resource allocation graph, you are getting that. Okay, so in case if a cycle is encountered, the system is in deadlock state, and if it is in deadlock, the cycle is also forms. But if a multiple instances of each resource type is there, then already we defined that, okay, cycle does not guarantee that the system is in deadlock, but deadlock leads to a cycle. That's why in order to work on multiple instances of each resource type, then we go for Banker's algorithm. Already in resource allocation graph, already in a resource allocation graph, we're already seen that. Okay, there are two types of edges are there in resource allocation graph. Number one is requesting. Number two is assignment edge. Number one is requesting edge. Number two is assignment. Requesting edge in the sense process PI is requesting for a resource RJ. Next, in case if you're having assignment edge in the sense of RJ to PI, if you have an edge from RJ to PI, that implies RJ resource is already assigned to process PI. This is what you have. And apart from these two edges, okay, this Banker's algorithm is introduces another edge is going to be called it as claim edge. Another edge is going to be called it as claim edge. So what is this claim edge? So in future, the process, suppose in case you happen to put an edge PI to RJ, that implies in future the process PI may request a resource RJ. This particular claim edge are going to be represented with the dashed line, that is dotted lines. And you please try to see that by making dotted lines, in case if the cycle is forms, that implies the system is in deadlock state, you are not in a safe, so that this particular claim edge cannot be sanctioned. So first of all, the process must be requested for a claim. In case if it is not causing any particular cycle, it does not causes any cycle, allow them as a requesting edge. And after that, this requesting edge, once the resource is available, it converted into an assignment edge. It is converted into assignment edge. Okay, this is how the edges are going to be done. First of all, a process must be claim a particular resource by using claim edge, and in case by adding claim edge to your resource allocation graph, it does not forms any deadlock, then allow them to convert this particular one into requesting edge. Okay, once the resource is available from the operating system, this request edge now converted into assignment edge. This is how it is going to be done. And that implies, what is the meaning of this? So you should have priority information about each and every process, at what moment of time every process is requesting for resources. In case if such kind of an information is not available with you, you cannot able to define a proper safe sequence. That is what is going to be. Okay. Okay, that implies, okay, your operating system should have a prior information about each and every process. Okay. So what kind of resources are going to be needed by each and every process at what moment of time? At what moment of time? This is what is. Now coming to the next very important one is that, now I'll explain you this is. So this is going to be called it as, how if you see, process P2 is requesting for a resource R1. R1 resource is already allocated to process P1. Process P1 in order also requires it is also requires okay, resource R2. This is also called it as claim edge. So let us take an example, an unsafe state in a resource allocation graph. So let us take an example. Suppose if let us assume this edge is not there. Okay, R1 is already holded by P1. So process P2 is requesting for a resource R1. Okay. And R2 is also is held by process P2 holding R2 and waiting for R1. R1 is already held by P1. Suppose in future the process P1 request for a resource R2. By putting this claim edge and you observe it, there is a cycle in your computer system. Yes, there is a cycle in this particular graph. Yes. Once it is cycle is formed, this edge is not converted into a requesting edge. Why? Because it leads to deadlock state. It leads to deadlock state. This is how we are going to be overcoming the problem. Okay, by putting a claim edge, you please try to observe that in case if the cycle is formed, that is your system is in unsafe state, that is your system is in deadlock state, please don't try to allow them to convert this claim edge into a requesting edge. That's it. Now, coming to the next very important one is algorithm. So already we told that suppose that if any process requesting for a resource after the request can be granted only if converting the request agent in assignment does not result in the formation of a cycle in the resource allocation plan. In case if it is forms a cycle, you please don't try to allow them to sanction. Okay, that's it. This is a general principle. Now, Banker's algorithm is in safe state, and this algorithm is divided into two algorithms. Number one, safe state algorithm. Number two is resource request algorithm. The safe state algorithm simply defines whether there is a safe sequence can be defined by your computer system or not. In case if the safe sequence is defined properly, then system is in safe state. In case if unable to define it, then it is in deadlock state. The resource request. Whenever a process is requesting for any particular new resources, whether it can be allowed to sanction or not, which will be decided by this particular resource request algorithm. So before going to these algorithms, okay, first of all, let us will see some of the assumptions, okay, or some of the points. Okay, I am assuming that first of all, there is a multiple instance of each resource type is available. Whatever the resources which is there in my computer system, I am assuming that there is multiple instances of each resource type is available. So, and second very important point what I need is that, okay, the operating system have a prior information about each and every process, what is the maximum need of resources of each process. Okay, each and every process must be specify what is the maximum number of resources which is required to compute my process. That is complete my process. Okay, so whenever a process has been requesting for any resource, first of all, it has to wait. First of all, it has to wait. Immediately, it cannot going to be granted. What I need to do is that, first of all, whenever you have been requested for any particular new resource, first of all, I need to observe that I need to make it as a claim edge. After claiming an edge, I see that whether it is going to be forms any cycle or not. In case if it is forms a cycle, it cannot be allocated. So in case not, if it is not forms any cycle, then a requesting edge may be, then your claim edge is converted into a requesting edge. Once the resource is available, then it is going to be converted into assignment. So that implies, so what my point is then, whenever a process is requesting for any particular resource, immediately it cannot be sanctioned. It has to wait for checking this process. And the very important point is that already you know that according to the system model, okay, once the process execution is complete, you need to return back all the resources what will have been sanctioned for execution of your process. So immediately after execution of your process, you need to return back all your resources to your operating system. This is the main points what you need. That is already we know these points. Why? Because already I told that what is a process. A process can be thought of as it is a program in execution. In order to execute such kind of a process, it may require resources like CPU cycles, memory cycles, IO devices, CPU registers, etc. But all these resources are under the control of an operating system. So before executing any particular process, first of all, you have to give a request system call for allocating resources. Once the resources has been allocated, you need to use that resources by using use system call. And once your process successfully completed, you need to return back all the resources to your operating system by using release system call. This is important. That's why we told. Now let us in algorithm. These are the data structures. What we are going to use is for deadlock to avoid deadlock situation. There is n number of processors running in my computer system. Okay, there is m number of resource types are available in my computer system. Now, so coming to this one, first of all, if anything, I haven't written available of j is equal to k. Available of j is equal to k. What is the meaning of this? There are k instances of rj type resources are available. There are at the same time. There are k instances of Rj type resources are available. That is the meaning. Maximum. What is this max? Max of I comma j is equal to k. Navya, water please. Maximum of I comma j is equal to k. In order to execute process pi, it is requesting k instances of resource type rj. In order to complete process pi, it is requesting for a resource rj of how many k. In order to complete process pi, it requires k instances of resource type rj is required. Allocation. What is allocation? It is also a two-dimensional array. Allocation of I comma j, that implies in order to now the process pi currently process pi currently process pi currently holds k instances of rj type resources. Process pi currently holds k instances of rj type resources. Need. So next one, need. So need of I comma j is equal to k. This is simply telling you that in order to complete the process pi, it requires k instances of rj type resources are required. That's it. So need is always defined as maximum minus allocation. Need is defined as maximum minus allocation. Need is always defined as need is equal to define. I'm upset everyone, mama. Sorry. Maximum minus allocation. Need is equal to maximum minus allocation. Now coming to the next one, safe state algorithm. Next one, safe state algorithm. Check. Online class. Now coming to the next one, safe state algorithm. Next one, safe state algorithm. What is this safe state algorithm? Now, I'm taking let work and finish be two vectors of length m and n respectively, and initialize the work is equal to currently whatever the resources which is available, and finish I is equal to false for all the variables. Finish I is equal to false for the all the variables. Now, so now find an I in such a way that finish I is equal to false. Find an I such that finish I is equal to false and it is not selected before, and need is which process need is less than or equal to work. Select such an I and allocate the resources. If no such I is exist, go to step 4. No such I exists, then go to step 4. After that, whatever the resources which is allocated for that process are successfully executed and return back all the resources to your operating system. Then work is equal to then work allocation. Now the finish I is equal to true. That process successfully ended. Go to step 2. Repeat this particular process until all process execution has been successfully completed and all the resources has been returned back to your operating system. If finish I is equal to true for all I, if finish I is equal to true for all I, then the system is in safe state. Then the system is in safe state. Otherwise, the system is in unsafe state. This is a safe state determination. This is safe state determination. Now, coming to the next one, resource request algorithm. Next one, resource request algorithm. What is this resource request algorithm? So, in case if any process requesting for any particular set of resources, first of all, we must check that. Whether the request is less than or equal to its original need or not. In case if it is not like that, given error conditions, the process is exceeding its maximum claim. The process is exceeding its maximum claim. In case if the request I is less than or equal to need I, then you need to check that whether the request is less than or equal to available, whether the request is less than or equal to, whether the resources is currently available or not. We need to check it. In case if it is available, then whatever the resources which has been requested, once it is sanctioned, available is becomes available minus request. And what are the resources which has been already allocated that particular process? It is added with this particular request, and the need is only whatever presently which is sanctioned must be subtracted. Need is equal to need minus request. Need is equal to need minus request. That's now this particular problem can be understood by taking a suitable example. That is, we'll take one particular problem and we need to determine the safe sequence and in what sequence we need to allocate the resources so that the system is in safe state. Whether the system is in safe state. Whether the system is in safe state. Let us take, there are 5 processes are running in my computer system. Okay, there are 5 processes are running, that is P0 to P4, P0, P1, P2, P3 and P4. There are 3 resource types are there, A, B, C. There are 10 instances of resource type A. There are 5 instances of resource type B. There are 7 instances of resource type C required. Now, whatever the resource request is at snapshot at time P0, just a moment of time, I'll bring a glass of water. Now, there are 5 processes are running in my computer system. There are 5 processes are running in my computer system. That is P0 to P4. Okay, and there are 3 types of resources are there, A, B, C. There are 10 instances of resource type A and 5 instances of resource type B and 7 instances of resource type C. That is okay, at time T0, these are the requisitions of a particular process. In order to complete this table simply shows that in order to complete process P0, it requires A type resources 7, B type resources 5, and C type resources are 3. In order to complete process P1, it requires A type 3 and B type 2 and C type 2. In order to complete process P2, it requires A type 9 and B type nothing and C type is 2, so on up to like this. The currently available resources are A, B, C. The currently available resources P0, P1, P2, P3, P4. The currently allocated is P0 is already holds 1 instance of B type resource, and process P1 holds 2 instances of resource type A, and process P2 holds 3 instances of resource type A and 2 instances of resource type C, and process P3 holds 2 instances of resource type A and 1 instance of resource type B and 1 instance of resource type C. and so on up to like this. Okay. Now, so correspondingly, now you calculate what are the resources already consumed by each and every process. Now, first of all, okay, you need to first of all you need to calculate. This is A type resources consumed by P1 2 and P2 is 3 and P3 is 2. Totally 7 are consumed, and B type is 2 and C type already used is 5. Now the total 10 minus 7. A type is, there are 3 instances of A type resources available now. So 5 minus 2, that is 3. Okay, there are 3 instances of resource type B is available. 7 minus 5, there are 2 instances of resource type C is available. There are this is the currently available. Now we need to calculate what is the need of each and every process. How do we calculate need? Maximum minus allocation. Maximum minus allocation. 7 minus 0, 7. 5 minus 1, 4. 3 minus 0, that is 3. Similarly, P1. Yeah, P1 requires A type resources 3, but already allocated with 2, so that 3 minus 2, it requires only 1 additional resource. So 2 minus 0, 2, 2 minus 0, this one. After calculating all this, then this is what is the need of each and every process. This is the need of each and every process. So, yeah, in order to complete process P0, it requires A type resources 7, B type is 4, and C type is 3. In order to complete process P1, it requires A type 1 and B type 2 and C type 2. In order to complete process P2, it requires A type 6, B type 0, and C type is 0. So on up to like this. Now, coming to the next very important thing. Now, the currently available resources, we have only 332. Now you observe it, 332 is satisfied by process P0. No. Why? Because it requires A type 7, but we have only 3. Okay, that's why it is not satisfying. Now we'll see that P1. So P1 requires only A type is 1, but we have 3, no problem. Okay, and B type it requires only 2, we have 3, no problem. And we have P1 requires, okay, 2, we have 2. So that now, in case if you go in a first in first out manner, okay, in a queue manner, so that currently P1 is satisfying. Similarly, P3 is also satisfying. So you may not have only a single safe sequence, you may have multiple safe sequences. Now, 1 to 2. So whatever the currently resources which is available to this particular one, okay, now it is initially allocated to process P1. Initially it is allocated to process P1. Whatever the resources which is already allocated to them, so you observe it, already P1 is allocated with 200. So that resource is going to be simply released. So released in a sense according to release system call. According to release system call. According to release system call, now whatever the resources which has been already allocated, which is returned back to your operating system. So that is 3 plus 2, it becomes 5. 2 plus 0, that is, this is a small wrong. Okay, I'll check it with already 200. Already 200. This is 3. This is 3, a small error. Let us make a correction. Let's make a small correction in this. This is 3. This is 332. So now the currently available is 332, already allocated 200, add together 3 plus 2, 5, 3 plus 0, 3, and 2 plus 0, this is 2, 532. And after that, next one, the currently available resource is 532. Now this value available becomes here 532. Now it is satisfying whom? So it is not satisfying P0, but P1 is already completed. The P2 is required 6 resources, but currently available is only 5. It is not satisfying. Now we'll take for P3. So the P3 is 011. That is, it requires B-type resource 1 and C-type resource 1. That implies, but we have 532. So the currently holded is, so P3 is satisfied. So P3 is already held up with how many resources? 211. So according to release system call, that the resources has been released. Now the currently available is becomes 5 plus 2 7, 3 plus 1 4, 2 plus 1 3. That's it. This is what is going to be. Now coming to the next one, the currently available is now 743. Now again check it. It is satisfying. Okay, P naught is satisfied. So that allocate all the resources this one. Then the resources now becomes already allocated should be added to this. That is 010. That is 753. Now again 753 is satisfying whom? It's satisfying P2. Now allocate all resources to P2. So that now available becomes 7 plus 3, 10, 5 plus 0, 5, 3 plus 2, it becomes 5. Now coming to the next one. Okay, coming to the next one. P4. So that is 10, 5, 5. It is now already it is allocated with 002. Now it added with, now all resources have becomes idle now. So this is what are the set of resources which is available in us. It should be allocated in this sequence, that is first P1 followed by P3 followed by P4, P2 and P0. In case you allocate the resources in this particular manner, the system will never enter into the deadlock state. So this is going to be called as safe sequence. Okay, and note that the safe sequence may not be unique. Okay, the safe sequence may have any number of safe sequences. That's it. This is what it is. In case if you properly define this particular safe sequence, the system is in safe state. Otherwise, the system is not in safe state. That is what we have been written in this algorithm. Have you observed this? This is initially let work and finish be two vectors. Let work can be finished with work. Work is equal to available. Currently, what are the resources which is available? Okay, first of all, take all these particular resources as work. This is the work that should be eligible for doing by your operating system, and finish I P0, P1, P2, P3, P4, and all are initialized as false. Now you need to find an I. Okay, you need to select any one of the process, that is flag is equal to it finish I is equal to false. Okay, whoever the need is less than or equal to work, and whoever the need is satisfying currently available resource, you need to find an I in such a way. After finding that an I, if you're unable to find it, then simply the system is in deadlock. Otherwise, okay, so work is equal to work plus, that is equal to available is equal to available plus allocation. So, and make it that finish is equal to true. Next time in selection process, this particular one is not in competition. Why? Because we are finding an I in such a way that where finish I is equal to false. That's enough. After making all this, if we see that if finish I is equal to true for all the processes, then the system is in safe state. Otherwise, the system is not in a safe state. Now, coming to the next one, resource request algorithm. If any process is requesting for a resource, first of all, you need to check that whether the request is less than or equal to their original need or not. If it is original need, okay, in case if the process is requesting, it is not satisfied, then the process is requesting its maximum claim. So already I have been told that in order to implement this particular deadlocks technique, Banker's algorithm, the process operating system should have a prior information about what is the maximum number of resources which is required and what moment of time each and every resource is required. It should be known. In case if the request is less than or equal to need I. Next one, we need to check whether the request is less than or equal to available. Whether the request is less than or equal to available. Whether the request is less than or equal to available. Request is less than or equal to available. In case if it is not available, so we cannot do it. So ask him to wait. In case if request is available less than or equal to available, then available resource becomes available minus request. Already allocated becomes allocation plus request, and need is equal to need minus request. This is what we have been saying. Now this is what I mean by deadlock. Now coming to the next very avoidance techniques. Now coming to the last topic of discussion in this, deadlock detection. Now, if a system does not employ, if a system does not install with either deadlock prevention or deadlock algorithm, then definitely there is a deadlock in your computer system. So, in case if your computer system is not implemented with any kind of deadlock prevention or deadlock avoidance mechanisms, In case it is not having any deadlock algorithms, then the system definitely enter into a deadlock state. Once a deadlock is encountered, what you need to see? So then if it is both are not done, the system must be entered into a deadlock. So the system is allowed to enter into the same state of mode. So now deadlock. Then what do you need to do? Then we need to go for deadlock detection techniques. The deadlock detection is techniques allow the system to enter into a deadlock state, and by using a recovery algorithm, it will be bring back to safe state. Okay, in case if your computer system not employing with either deadlock detection or a deadlock avoidance, it should have deadlock detection mechanism. And deadlock detection, you need to provide at least two algorithms. One algorithm you use it to check whether the system is in deadlock state or not. And second step, in case the system is in deadlock state, the system is in deadlock state, you need to use an algorithm to break the deadlock. That is a recovery from the deadlock. Now, how do you explain this particular concept? Earlier, we have been described the deadlock characterization by using resource allocation graph. Here also we use the same resource allocation graph. So additionally, we are also constructing wait for graph. In this particular wait for graph, there is only processes are as vertices. Only processes as vertices, or I call it as nodes. And edges are only like this, Pi to Pj. This is, what is this? What I mean by this? Process Pi is requesting from set of resources which is already held by process Pj. In wait for graph, we are representing process to process edges. That implies process Pi is requesting for a set of resources. This particular resources is already held by process Pj. Understood, everyone? This is process Pi is waiting for the resources held by process Pj. That's it. So now, what do you need to do? So after saying earlier, whatever the principles we have been seeing in resource allocation graph, the same techniques. In case if each resource type is a single instance, cycle leads to deadlock, deadlock leads to cycle. And point number two, in case your computer system is having more than one instance of each resource type, then cycle may not guarantee that system is in deadlock state, but deadlock is always having a cycle. Then what you need to do internally, we need to periodically, okay, invoke an algorithm that searches for a cycle in the graph. If there is a cycle, then we can register deadlock. That's it. So we need every moment of time. So you need to set some time, some amount of time periodically, and you need to check whether the system is in deadlock state or not. An algorithm to detect a cycle in a graph is an order of n square. That is n square. That is the time complexity for checking whether the system is in deadlock state or not. Is simply order of n square. You know what is time complexity? The time complexity is simply defined as the time it will going to be taken for executing an algorithm or a program, or you may call it as, okay, the second definition of a time complexity is the basic statements, basic number of statements which is executed in a computer system is time complexity, or you may define it as number of comparisons, where this n is representing the number of edges in a graph. We need to check all the edges. That's why, suppose if a graph is having 4 edges, 1 1 1 2 1 3 1 4 4 2 1 2 3 2 4 3 1 3 2 3 4 4 1 4 2 4 3, so on up to like this. We need to check for all the edges. That's why the time complexity is order of n square. We got one bit. Okay, what is the time complexity for detecting a cycle in a graph while doing deadlock detection? The time complexity is order of n square. Now, so let us see. This is a resource allocation graph. The corresponding wait for graph is demonstrated like this. Please observe it. Now, first of all, I am demonstrating it. This is a resource allocation graph. In a resource allocation graph, the vertices, or may call it as nodes, are represented with either processes, or may call it as resources, processes, or may call it as resources, processes, and resources. Okay, so now process P1 is holding R2 and waiting for the resource R1. R1 is already held by P2, and P2 is requesting for a resource R3 and R4, and P5 is holding R3, and so on up to like this. So this is P1 is requesting for R1, It is a requesting edge. R2 is already allocated to P1. This is an assignment edge. Now, how to construct a corresponding wait for graph from a resource allocation graph? Now, in wait for graph, we are having only process to process edges. And the second very important one is that we're having only process as a vertices. I might call it as nodes, process as a nodes, and there is only one type of edges are there. How do you know? You know that this is an edge indicating that process P1 is requesting for a resources which is already held up by P2. Similarly, process P2 is requesting for a resources which is already held by P5. So on up to like this. How to construct this particular wait per graph from the resource allocation graph? From this resource allocation graph, let us take an example. If process Pi is requesting for a resource Rj and Rj is already held by Pk. You understood everyone? Pi is requesting for resource Rj. Rj is already held by Pk. Then you need to put an edge from Pi to Pk. Then you need to put an edge from Pi to Pk. Now you see this. P1 is requesting for R1. R1 is already held by P2. Now whatever the resource which is requested by P1, which is already held by P2, so that you need to put an edge from P1 to P2. This is how to put an edge. Now P2 is requesting for a resource R3. R3 is already held by P5. Now whatever the resources which is requested by P2, which is already held by P5, that implies you need to put an edge from P2 to P5. P2 to P5. P2 is requesting for a resource R4. R4 is already allocated to process P3. Then you need to put an edge from P2 to P3. You need to put an edge from P2 to P3. Like this, you need to construct. Once this wait for graph is constructed, the same principle. Okay, in case if it is a single instance of these resource type, that is cycle causes a deadlock and deadlock causes a cycle. In case if the multiple instance of each resource type is available, then so cycle may not leads to a deadlock, but deadlock leads to a cycle. But deadlock leads to a cycle. Now we'll go to the algorithm. There is several instances of each resource type. Earlier, what we have data structures we have maintained same available j is equal to k. That implies there are k instances of Rj type resources are available. Allocation of I comma j is equal to k means that process Pi is already having k instances of Rj type resources are available. Similarly, request of I comma j is equal to k. That means in order to complete process Pi, it requires k instances of Rj type resources are required. Same earlier in Banker's algorithm, whatever the data structures we have been defined, the same kind of data structures also used here. Okay, now deadlock detection. So I have not written any separate algorithm for this. Okay. Okay. Now already earlier whatever the algorithm we have been written, the same algorithm. Let work and wait finish be two vectors of length m and n respectively. Initially whatever the resources currently available, make it as work, and for I will not whatever the process which are there. Initially finish I is equal to false. Finish I is equal to false. None of them has been selected. You need to find an I in such a way that finish I is equal to false, and whatever the resources which is currently requested, it should be less than or equal to work. It should be less than or equal to work, which is should be less than or equal to work. If no such I is just go to step 4 and see that whether it is all or any one of them is false. Now the system is in deadlock state. Otherwise, work is equal to work plus allocation. Whatever the resources which has been allocated to that particular process, which is written back to your operating system so that the total work is increased. Then the process is successfully completed so that you make them as true. It is not in the computation but next selection. Go to step 2, repeat this particular process until all finish I is equal to true. In case if any one of the finish I is equal to false, then the system is in deadlock state. If any one of them is false, then the system is in deadlock state. The system is in deadlock state. That's okay. And this is also requires m into n square. Why? Because every time we need to check that Okay, the work vector with all edges. That's why that is the algorithm requires m into n square. That is the time complexity for detecting whether the system is in deadlock state. In deadlock detection, algorithm is m into n square. In case if it is a single instance of each resource type, then you require only order of n square operations. Now, by using the above algorithm, suppose you have been observed that the system is in deadlock state. By using the above algorithm, now you have been observed that the system is in deadlock state. Now, how can you how can you recover the deadlock? The recovery from a deadlock, there are two options for breaking a deadlock. There are two options for breaking a deadlock. Now, the first solution is that simply abort one or all process to break and the circular wait. The first solution is that simply abort one or all processes to break the circular wait. Number two, preempt some resources from one or more deadlock processes. Preempt one or more processes. These particular techniques are going to be classified as number one, process termination. Number two, resource preemption. These are the two types of solutions what we have to recovery from a deadlock. Okay, now coming to the first very important one is that process termination. What do you mean by process termination? Okay, abort one process at a time and see that whether the deadlock is eliminated. In case it's not eliminated, remove another process, abort another process, repeatedly do until the deadlock cycle is eliminated. That is simple. Abort one process at a time until the deadlock has been removed from your system. Number two, otherwise abort all deadlock processes. Abort all deadlock processes. That's simple. Second solution, resource preemption. Resource preemption in the sense we are not stopping or reporting any one of the process. So resource preemption in the sense whatever the set of resources which has been already sanctioned, whatever the set of resources which is already held by that particular process, please get all the resources back. Please get all the resources back. Okay, and once the deadlock is eliminated, again or later that we can allocate them. This kind of a process called as resource preemption, which can be done by using three techniques, three steps. Selecting a victim. First of all, we need to see that which process is having a less priority. Selecting a victim. Roll back whatever the resources which has been already sanctioned. Okay, please try to get back and restart the process at a later stage. And there may be a chance that every time this process may be restarted, then this particular process is going to enter into starvation. In order to welcome this particular starvation, we use aging concept. Suppose if the process has been rolled back for first time, then it periodically some by something incremented. After again second time this process is again preempted, then again its process priority is going to be incremented. So on up to like this. At any moment of time, it maybe becomes one of the highest priority, so that it's not going to be suffers from this kind of a concept. You already know that aging. What is aging? Aging is a concept continuously adding priority for the waiting processes. That's so. From this, we have been concluded the process management topic. Is it clear, everyone? So in process management, totally we have been concentrated on process scheduling, process synchronization, and deadlocks. So you please try to go through the problems what I have been discussed. That is in process scheduling and process synchronization and deadlocks. Definitely you are going to be getting more than 2 questions from these 2 topics, from these 4 topics. Is it clear? Now we'll move on to the next topic. This is completes our discussion about process management. Now we'll move on to memory management. Already I told that what is an operating system. An operating system is a collection of various components. What is those components? Process management, memory management, IO management, protection, secondary storage management, security, command interpreter system, etc. So we have been completed about process management. Next, we are going to be moving on to memory management. So before going to the detailed discussion about this particular memory management, what we are going to learn. So first of all, we'll taking about first of all concept of discussion is memory management techniques. What is memory management techniques? And second topic is virtual memory. We'll see. Now coming to the memory management techniques, you already know that whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. So how do you copy that program into memory, and where you need to copy, how to manage your program, this kind of a techniques is going to be discussed in the first topic of discussion. The second topic of discussion is that virtual memory. What is virtual memory? A virtual memory is an illusion. A virtual memory is a concept which gives an illusion to the programmer that he has a large amount of memory, relatively having a small amount of memory. Even though if you have a small amount of memory, it's giving a look and feel that you have a large amount of memory. So that is going to be called as virtual memory. So let us take an example. Now let us take an example. Suppose if you want to run a program, okay, that is of 8 KB space is required, but the memory is having 20 KB. Is it possible to run the program? Yes. Why? Because 8 KB is okay, 8 KB required, but you have a 20 KB of memory space so that you can run it no problem. Now, suppose if you want to run a 25 KB program, but you have available space with only 20 KB, is it possible? Everyone says that no, and yes, it is possible. How? By using paging and segmentation with paging. By using this particular concept, you can run a 25 KB program by fitting in 20 KB of memory. That's why if any guy, if any third party person, if simply understood that 25 program is run, yes, there is a 25 KB memory is minimum available for you. No, the memory available is only 20 KB, but you can run 25 KB. That implies it gives an illusion to the programmer that he has a large amount of memory, relatively having small amount of memory. And such kind of a concept is going to be called as virtual memory concept. Let's take an example. Suppose you have written a one program. The program is having 5 or 6 functions followed by main program. You are not executing all functions at the same time. Yes. So first of all, we'll copy the main program into main memory. First time, while executing main program, if any function is required, it is going to be copied at the time of execution. And once execution is successfully completed, again you need to remove it back from the memory. Like this, we can run a 25 KB program by fitting in 20. That's why it's called as virtual memory. So in order to practically implement this virtual memory concept, we have the following techniques: paging, segmentation with paging. We'll say at a later stage. This is the topics what we are going to be seeing in this. Now coming to the first one, what is a memory? Coming to the first topic of discussion is the memory. First of all, how do you define a memory? A memory is simply defined as it is a large array of words, or you may call it as bytes. Each and every one is having its own address. The CPU is going to be fetching the instruction from the memory according to the value of program counter. You know what is program counter? Okay, already we told that what is a program counter. So program counter is initially, it is a special type of register. A program counter is a special type of register which is initially containing the starting address of the program where your program execution is going to be started, which is initially contains the starting address of the program where your program execution is going to be started, and after that it contains what is the next line is going to be executed. This is what is program counter. So that's why, so memory is going to be simply defined as a large array of words or bytes. Each and every word is having its own address. The CPU will going to be fetching the instructions according to the value of program counter. And the next very important thing is that before going to the detailed discussion about, before going to the detailed discussion about, the memory management techniques, first of all, we need to see that, address binding. So what are the different kinds of addresses which are associated for your program? So whenever the user is trying to execute any particular program, what are the various kinds of addresses which is associated for your program? Already you know that the collection of processes on a disk that are waiting to be brought into memory for execution is going to be always in the form of a queue. Already this kind of a queue is going to be called as job queue. That is the set of all jobs which are residing on a secondary storage device, which is ready to come into memory, are going to be called as job queue. Then your job scheduler is selecting some of the jobs from secondary storage device to main memory. Is it clear? That is the first very important one. And before going to this particular different kinds of addresses, you already know that. Swapping. What do you mean by swapping? Swapping in a sense, please try to remove a process from the memory and back into secondary storage, which is not currently required by the CPU, and bring the currently required process from secondary storage device to main memory, which is going to be done by your dispatcher, or which includes context switch. Listen, these two things you should be know. That's why initially I'm telling that. So initially all the jobs are going to reside in secondary storage device. And whenever you're trying to execute this particular jobs, first of all, this particular jobs must be comes into main memory. Now, that is the first one. Now, coming to the topic of discussion is address binding. So in address binding, first of all, you must know that absolute address and relocatable address. You must know this pattern. Already we told these concepts is covered in topic 3, that is in operating system structures. In operating system structures, already I told that the protection is done by using base comma limit registers. Protection is going to be done by using base comma limit register. Protection is going to be done by using base comma limit registers. Now, so coming to the first one. So before defining what is an absolute address and what is relocatable address, okay, absolute address is also known as physical address. Relocatable address is also known as logical address. In order to understand these particular two addresses, so we will demonstrate it by using a small problem example. In order to understand this, first of all, let us will define what is relocation. What is relocation? A relocation is a process of moving your program segment from one particular memory location to another location. What is relocation? Relocation is a process of moving your process from one particular area of memory to another area. So relocation is a process of why you need to relocate to overcome external fragmentation. I told in the earlier, what is external fragmentation? Required amount of memory is available, but it is not in a continuous form, so that you cannot able to execute the process. That's why you can call it as external fragmentation. The required amount of memory is available, but it is not in a continuous space, hence the user cannot able to run the process, which is called as external fragmentation. In order to overcome such kind of a thing, what we need to divide is that so relocation. So we need to do is not talk about relocation. Relocation is nothing but moving a process from one area to another area. Let us take an example. My process is running in an area like this 300000402 like this. Now the address of each and every instruction is like this 30040404142 so on up to 420940 like this. Suppose this address is called it as absolute address. Original physical address is going to be called it as absolute address. Suppose if you make absolute addressing scheme like this, suppose due to fragmentation problems, if the program is moved from one location to another location, suppose if the program is moved from this location to some another location, you need to do two things. Number one, you need to copy all the instruction from this area to this area. and you need to change each and every instruction address. 3000 for 3 lakhs 40, 3 lakhs 41, 3 lakhs so on like this. Now you need to change that 8 lakhs 80,001, 8 lakhs 80,002, and so on like this. Copy is a compulsory activity, no one can eliminate it, but the most of the processing time is wasting for changing the address of each and every instruction. In order to overcome this problem, now the address has been split into two parts. The address is being split into two parts. Number one, base and offset. The address is defined as base and offset. Now the base address is defined as 3 lakhs 40 is stored in base register. Now the offset addressing is given as 1, 2, so on up to 1,20,900. Like this you are given. Your the address is here 1, 2, so on up to how much? Okay, 1,000 to 1,20,900. You need to give. How do you get original address? Content of base register, that is 3 lakhs 40 plus 1, 3 lakhs 41, 3 lakhs 41 plus 1, 3 lakhs 42, so on up to like this. Content of base register plus offset is equal to this one. Like this you are getting. What is the advantage of splitting the address into two parts? So by splitting the address into two parts, if your program is moved from one particular area to another area, you need not change each and every instruction address. This address is 0, 1, 2, so on up to 12,000. Sorry, 1,20,900. Instead, same addresses you can give 0, 1, 2, so on up to 1,20,900. You can give it, and only the base address is instead of 3 lakhs 40. Now you can store it as 8 lakhs 80,000. That's the relocation is possible simply by changing the content of base register. The relocation is possible only by changing the content of base register. Now this is physical address, or may call it as absolute address. These addresses are absolute address. 0, 1, 2, so on up to 1,20,900. These addresses are called it as offsets, or may call it as relative addresses. These are called it as relative addresses. Now the protection is going to be done. Already you know that base comma limit registers. How execution is done in the sense CPU generates always a logical address. CPU always generates a logical address that consisting of first of all you need to check that whether that address value is greater than or equal to base address or not. Whether the address is generate a base address or not. In case it is greater than base address, next we need to check that whether this process is accessing a legal area or other process area. That implies, how do you check it? Okay, and first of all, whatever the addresses which is generated by CPU, first of all it checks that whether the value is greater than or equal to base. If it is not greater than or equal to base, you are illegal, trap or an interrupt, simply you are stopping the execution of that process. And after that you need to check that base plus limit value should, whatever the addresses has been generated here, this address should be less than base plus limit. Why? Because why less than? We are starting with 0. Okay. Now coming to the next one. In case if it is less than, should be greater than or equal to base, and less than base plus limit, then your legal address you can eligible for executing a process. That's this is how it is going to be done. Okay, so this is original address, this is physical address. It should be greater than or equal to your base and less than base plus limit, then only it is a legal value. Now this is going to be called it as first of all absolute address and relative address. Now what are the other addresses are there? Other addresses is you also have compile time address, load time address, execution time address. Now we'll see what is these addresses. Now this is a topic is referred as address binding. This topic is referred as address binding. Now, so before going to the different definitions of compile time address, load time address, and execution time address. Okay. Now, so are all of the three are same? No, these are all different. Already we got one question from GATE whether compile, load, and execution time addresses are equal. They are given different options. Compile time address is equal to load time address and not equal to execution time address. In some question, compile time is equal to execution time but not equal to load time address. Like this they have been given. But the answer is compile time address is not equal to load time address, is not equal to execution time address. What will be? We'll see now. Now let us see. So initially you haven't written one program. Okay. So the programming has been generally the people are written in high level language, but your computer system should not be okay understood your high level language programs, so that you need a translator which must be responsible for converting high level language programs into machine language. Who is that guy? That is done by compiler or assembler. Okay, a compiler is a program which takes a high-level language program as an input and converts into a, a compiler is a program which takes a compiler is a program which takes a high-level language program as an input and converts into machine language. But internally, high-level language program is not directly converted into machine language. It is first of all converted into assembly language, and after that, assembly language is going to be taken by your assembler, and it is converted into machine language. So that is your object module. So in order to convert, and after that we'll see first of all. And after that, this object program is going to be taken by your linker. The linker is going to be simply responsible for whatever the necessary files which is going to be required to run this particular process. All object modules has been linked to this particular one. Okay, and after that it is given to your loader. Okay, then it is going to be given to loader. So in a loader, what is a loader? A loader is a program which takes your machine language programs as an input and loads that particular program into main memory and preparing for execution. Preparing for execution in the sense, please try to set the starting address of the program to program counter for initiation of execution. Please try to set the starting address of the program, okay, for initiation of execution. This is what is going to be done. This is generally whenever the user is, first of all, initially that is translation procedure has to be done. After translating, the program should be loaded into main memory and set the starting address of the program to program counter for initiation of execution. Now we observe it. While in case if you want to, whenever the user is trying to execute any particular program, first of all, it should be in machine language. Why? Because your computer can understand only one language, which is called it as machine language. Whatever the programs you are writing, these all programs are in high level language. So that you need a translator which must be responsible for converting high level language programs into machine language. Who is that guy? Compile them. At the time of compilation, wherever your program has been copied in main memory, at the time whatever the addresses we got, that addresses is going to be called it as compile time addresses. That addresses are going to be called it as which is completely compile time addresses. That is absolute addresses, which is also absolute addresses. Okay, so now whenever the user is trying to execute that particular program, this program should be, again, once it has been compiled, it is very important point is that once your program has been compiled, that is translated into machine language in sense .exe executable file. Again, this executable file is copied back onto secondary storage device. Okay, it is not resident in memory. Your executable file is again back onto secondary storage device. Whenever the user is trying to execute this particular program, this executable file is going to be copied into memory. So I am not guaranteed that earlier in what area the program has been compiled, the same area may be now available or not. I don't know. It may be copied in some other area. That's why the load time, whatever the addresses we have been got at the time of loading the program in memory, is going to be called as a load time addresses. That's why it is a relocatable address. It is a relocatable. Relocatable in the sense you need to divide them into base plus offset. But relocatable. At the time of execution, whatever the program you have been copied in the area, it may not be reside in the same area until the execution is complete. Why? Because due to fragmentation problems, your program may be moving either towards up or down, which is going to be called it as a relocation, So at the time of relocation, again, whatever the addresses we have been got at the time of execution, those kind of addresses are going to be called as execution time addresses, or may call it as a runtime addresses. That's it. So okay, so in compile time, you're getting absolute code. At the time of loading and execution, you are going to be getting relocatable addresses. Okay, please try to understand this. We got so many questions in GATE by using this. And this concept is very, very important. You'll get 1 mark question on this. Okay, and finally, I conclude that compile time addresses are not equal to load time addresses, not equal to execution time addresses. So whatever the addresses we have been got at the time of compilation, that such kind of addresses are going to be called as compile time addresses. At the time of execution, Load time, whatever the addresses has been generated by your computer system is going to be called it as load time addresses. At the time of execution, whatever the addresses we have to got, such kind of an addresses are going to be called it as execution time addresses. This is what is address point. Now, so coming to the next very important one. Okay, overlays concept. It will demonstrate it by using a small problem example. Okay, what do you mean by, first of all, before going to the detailed discussion about static, okay, overlay structure, now we are going to see what do you mean by static loading and static linking, and what do you mean by dynamic loading and dynamic linking. First, we'll see this part down. Now, coming to the first one. If the loading and linking activities are going to be done at the time of compilation, if the loading and linking activities are done at the time of compilation, if the loading and linking activities are done at the time of compilation, then it is going to be called as static loading and static linking. If the loading and linking activities are postponed until their execution, then it is going to be called as dynamic loading and dynamic linking. Good. Now let us see the example. Now we'll see my means an example. Suppose if the main memory capacity is 20 KB, I want to run a program which is of 8 KB. Is it possible to run? Yes. So that program is going to be totally loaded 8 KB. Now I having 20 KB of program. There is no problem. I can load all the program modules at the same time. I can run it. So the loading is done at the time of compilation. Hence it is called as static loading. And what are the necessary files which is going to be required to run that particular process? It is going to be linked at the time of compilation itself. Then it is going to be called as static linking. Now, suppose if the main memory capacity is only 20 KB, I want to run a 30 KB program. This is not possible. So, by using virtual memory concept, I can run a 30 KB program by fitting in 20. So, the behind principle is that what are the necessary modules are required is going to be loaded at the time of execution according to the requirement. That is, the loading is not done at the time of compilation. It is going to be done at the time of execution. That's why it is called as dynamic loading. Loading is done at the time of execution. Okay, if linking is also done at the time of execution, that is called as dynamic linking. That implies the loading and linking activities are done at the time of compilation is called as static loading and static linking. If loading and linking activities are done at the time of execution, then it is going to be called as dynamic loading and dynamic linking. So now, how these dynamic loading and dynamic linking concepts are internally implemented. So this is already done by using driver stub concept by using stub. So first of all, main program is loaded with all stubs. That is all dummy modules are loaded. Only begin and there is no code is copied. At the time of execution, which function has been called, that function is going to be loaded at the time of execution. And once it is loaded, once it is executed, again it is removed from the memory. Like this, you are going to be done, which is called as dynamic loading and dynamic linking, which is going to be called as dynamic loading and dynamic linking. Now, how this can be demonstrated by using overlay concept. We'll see now. Suppose I am executing a 2-pass compiler. You know what is 2-pass compiler? You're already well familiar with compiler design. In 2-pass compiler, the entire compilation process is going to be done in 2 phases. In pass 1, you are simply collecting all the forward reference variables, and all forward reference variables are going to be stored in symbol table. In pass 2, while executing that kind of an instructions, in case if any forward reference address is required, that address is going to be taken from symbol table and substitute and continue the execution. So pass 1 is responsible for simply, number 1, generating a symbol table. In pass 2, we are generating into machine code. This is what we are doing. So in order to run a 2-pass assembler, we require the total amount of memory that is going to be required is, in order to run the pass 1, it requires 70 KB of memory. In order to run pass 2, it required 80 KB of memory in order to run in order to store symbol table. Okay, it required 20 KB. Common routines is going to require 30 KB. Okay, the total amount of memory to run a 2-pass assembler is 200 KB. The total memory which is going to be required to run this one is 200 KB. But the problem is what I'm having is only the total amount of memory which is available for me, only 150 KB is available for me. But how can I run? In order to run a 2-pass assembler, the minimum amount of space which is going to be required is 200 KB is required. But my main memory capacity is only 150 KB. How it is possible? Now what I'm doing is that, first of all, I load the symbol table which is of 20 KB. Common routine says 30 KB. Overlay driver, it is of small program. We'll see what is this. I'll define it later stage, which is of 10 KB. And the rest of the thing, okay, among 150 minus 10 minus 30 minus 20, totally 90 KB is available. And you observe it, pass 1 software and pass 2 software, that is pass 1 module, pass 2 module, both are not required at the same time in memory. Both pass 1 and pass 2 are not going to be required at the same time. Okay, pass 1 and pass 2 both are not required at the same time. Okay, so what I'm doing is that, first of all, pass 1 is going to be loaded in this area and it is successfully run. Once successfully running, I'll be removing this particular pass 1. In this, again, I'll bring pass 2 software here and run it. Like this, I'll run the program. That's it, it is over. That implies what happens is that after completion of pass 1, it generates a symbol table. Again, remove pass 1, bring pass 2 into memory. Using this pass symbol table, you generate a machine code. You know what is assembler? Assembler is a program which takes your assembly language program as an input and converts into machine language, and along with the information to the loader where this particular program should be loaded into main memory. Where this particular program should be loaded into main memory. Now, who is responsible for reviewing a process which is not currently required in memory and bring the requested program into memory? That is done by a small program known as overlay driver. That is done by a small program known as overlay driver. A overlay driver is a small program which is responsible for removing the processes which is not currently required and bring the requested process into main memory. This is overlay driver. So the total, I can run a 20 MB program by fitting in only 150 KB. The entire duty is going to be taken by your overlay driver. That's it. Now coming to the next one. Okay, logical address and physical address. Okay, already I told you what is the logical in the sense offset addressing is going to be called as a logical address. The entire address is going to be called as physical address. Okay, that's why I'm already defined you. Okay, in the earlier, the address is not going to be stored as a single part. It should be divided into base plus offset, base plus offset. That is this base address. This is logical address, or may call it as offset address. That says I have been told here. I'll give you the small introduction on this. The concept of logical address space is bound to the separate physical address space as a central property of memory management. So CPU is always generates a logical address, also referred as virtual address. CPU is always generates logical address, or may call it as virtual address. Original address seen by the memory unit is going to be called as physical address, which is also known as absolute address. Which is also known as absolute address. Logical and physical. Already I told that at the time of compilation, it generates only absolute addresses. You please clearly note that at the time of compilation, only absolute addresses are noted. That's why the logical and physical addresses are same in the compilation time. But so load time address binding schemes, okay, and logical and physical addresses differ in execution time. Why? Because at the time of compilation loading, logical and physical addresses are same. But at the time of execution, due to fragmentation problems, your program may be moving either towards up or down. At the time of execution, Okay, due to fragmentation problems, your program may be moving either towards up or down. Okay, that's why the logical then we in order to make such kind of a relocation, we are splitting the address into two parts, that is base plus limit. That's why the physical addresses are different at the time of execution. And hardware device is runtime. So your hardware device is responsible for converting a virtual address into original physical address. We'll see this kind of this is also known as mapping. That is going to be converting of higher order bit addresses into lower order bit addresses. Conversion of a logical address into physical address is known as mapping. We have a special hardware for converting a logical address space into physical address space. The value of relocation register is added to every address generated by user process at the time it is sent to the memory. Already I told that content of base register plus offset is giving you original physical address. The user program is always deals with logical addresses. It never see the original real physical addresses, which is only seen by your operating system itself. Your operating system hardware is responsible. In a computer system, there is a special hardware is there which is responsible for converting virtual address into original physical address. That's why whatever the address which has been generated by your CPU is going to be called it as logical address, which is going to be added to content of base register. Also call it as relocation register. You know that the relocation is possible simply by changing the content of base register. The relocation is possible simply by changing the content of base register or I call relocation. So 346 plus 14,000, this is original physical address. So whatever the addresses which is generated by CPU is going to be called it as logical address. That logical address is added to the content of base register or method is relocation register by the memory management unit, which is going to be gets you original physical address. Now, before going to the detailed discussion about the memory management techniques, first of all, just to reveal what the topics so far we have been already covered is going to be called it as swapping. You already know that. What is swapping? Remove a process which is not currently required in memory back into secondary storage and bring the requested process into memory from secondary storage device to main memory, which is done by a swapping program. A process can be swapped temporarily out of memory to a backing store and brought back into memory for execution, for continued execution. So you please try to swap out a process which is not currently required in memory and back into store for continued execution where it has been stored. So total physical memory space of a process can be exceeded when this swapping is done. The total physical memory that is going to be required to run that process is not sufficient. Then you need to swap out a process. Backing store. Fast disk large enough, okay, to accommodate copies of all memory images for all users must provide direct access to this memory images. Already I have been told that your IO processor is having a capability of directly storing and retrieving the contents from the secondary storage devices. Your IO processor is directly having a capability of storing or retrieving the data from the next rollout rolling. Swapping variant is used for priority based scheduling method. So we need to remove a process which is currently a low priority. So that implies while executing a low priority process, whenever a high priority interrupt is encountered, the low priority process is entered and the response is given to high priority process at the time. That is, the major part of swapping time is transfer time. The total transfer time is directly proportional to the amount of memory swap. The transfer time is directly proportional to. Now, system maintains a ready queue of ready to run the processes which memory images on the disk. Already I told that ready queue in the sense the set of processes which are residing in memory. The set of processes which are already ready in memory, which is waiting for the CPU to continue the execution, and such kind of process is going to be called as ready. Now, coming to the next very important point of discussion is that swapping. Now, when do we do swapping? A process needs to be in memory to be executed. A process, however, can be swapped temporarily out of memory to a backing store and then brought back into memory for continue the execution. Let us take a small examples for this. In round robin scheduling, once the time quantum is completed, CP is forcibly shifting from one particular job to another job. In that situation, we require swapping. And priority based scheduling, whenever a low priority process is running, a high priority interrupt is encountered. The low priority process is preempted, and the response is given to high priority process. In that situation, the low priority process is swapped out, and high priority process has to be comes into memory. Okay, and please try to see that while swap in swap out, you may not get in the same area. Again, the address binding has to be take place. Okay, at the time of execution, you may get a different types of addresses. Okay, that's why I told that execution time addresses or compound time addresses are not same. At the time of execution, the addresses are not always constant. The addresses may be changes due to swapping also. That's why one time we got a question in gate, and the execution time addresses changes due to the following reasons. At the time of execution, okay, the execution time addresses change due to the following reasons. A, due to relocation. B, due to swapping. Due to swapping. Okay, and C, both A and B, and D, none of the above. Answer is both A and B. Now, so who is responsible for doing this particular swapping? The dispatcher program is responsible for doing this. A dispatcher is a small program which stops the execution of one particular process and load a new process and start executing. This is all going to be done by your dispatcher. Already we know that the time it is going to be taken for stopping one particular process and giving the control of the CPU to some another process is going to be called as dispatch latency. Okay, this diagram shows that this process is swapped out from the memory and the high priority process P2 is possibly bring into memory. Now, so whenever a new process want to come into memory, if the memory is not sufficient for accommodating that new process, if it is a high priority, you need to remove any one of the process which is having a low priority that is back on the secondary storage. Now, which process has to be back in store? Which process has to be currently removed? So please, while implementing this particular swapping technique, okay, please try to see that, okay, some of the rules. Never swap out any particular process which is waiting for an IO operation. An IO operation, waiting for an IO operation process should not be removed from the memory. Okay, and the second very important constraint in this, to execute IO operations, only it should be done in operating system buffers only. So you cannot eligible for doing your area. All IO kind of, already I told you that all IO kind related transfers are always done by using buffers only. A buffer is the smallest, buffer is a part of main memory where your IO operations are rooted in. Okay, next one. For a modern operating systems, swap only when free memory is extremely low. For this is today what modern operating systems are going to be doing. Okay, this is what is meant by swapping. Now, coming to the next first very important technique is that memory management technique is that continuous allocation. So, before going to this particular continuous allocation, so everyone has to be keep one very important point on your mind is that whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. That is the first very important point you need to be kept on your mind. So please, okay, again I'm repeating the same point. Whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. That is the first one. Number two, whatever the amount of memory which is going to be required to run your program, the memory should be in continuous fashion. So let us take an example. Suppose you require 20 KB. In your memory, in one area you have 10 KB, and another area you have another 10 KB. You cannot run the program. Half program here and half program here, which is not possible. So whatever the amount of memory which is going to be required to run your program, the total memory should be in continuous fashion. Whatever the amount of memory which is going to be required to run your program, that memory should be in continuous fashion. That memory is in continuous fashion. That is the first very important thing. These are the 2 points you need to be kept on your mind before going to the detailed discussion about continuous allocation techniques. Now, main memory must be support both operating system and user processes. Okay, already I told you that one program is always runs in the system kernel, which is known as operating system. So when you are switching on a computer system, until then switch off, one program is always runs in the custom kernel, which is known as operating system. So that your main memory must accommodate at least 2 processes. That is, one is operating system, another one is user process. In this user processes, you can, according to multi-program, you can run more than one process. You can run more than one program at the same time. That is, the minimum number of segments which is required in main memory is 2 segments. Minimum number of segments which is required is 2 segments. And whatever the amount of memory which is having, this is a very limited number of resources we are having. So that whatever the set of resources we are having, you please try to allocate the resources in a very efficient manner. Otherwise, we cannot support multi-programming. You know what is multi-programming? So more than one program can be simultaneously reside in main memory, and during the execution of one particular program, in case if any programs required IO operation, CPU does not sit idle, it simply switches from one particular process to another process. Like this interleaved fashion of execution, giving a look and feel that all the jobs are going to be happening simultaneously. Interleaved fashion of execution, giving a look and feel that all the jobs are going to be happening simultaneously. This kind of a concept is called as multi-programming. So that whatever does, in case if you want to increase the utilization of a CPU, you need to increase the multi-programming. By increasing the multi-programming, so that you please try to allocate the memory in an efficient manner, otherwise it is not possible. Okay, so the continuous allocation is one of the earlier method. Of course, we are not using, but it is one of the traditional method what we're using. Now, so main memory is usually divided into mainly 2 parts. So in one part, your operating system is run. Okay, one part your operating system is always run in lower part of the memory. Operating system is always running lower part of the memory. That area cannot be touched by any one of the user processes. That area is completely protected. Okay, if anyone want to communicate with an operating system, that is always done by using system call. You already know that. What is a system call? A system call is acting as an interface between a process and an operating system. Whenever a process want to communicate with an operating system, that is always done by using a system call. Now, and coming to the next very important one is the user processes. Lower part of the memory is always allocated to operating system. The upper part of the memory, that is high memory, is always going to be given to the upper part of the memory is always given to the upper part of the memory is given for user processes. Okay, each process contained in a single continuous section of the process. So whatever the amount of memory which is going to be required, to run your process, it should be allocated in only one area. You cannot divide them into pieces, and one piece is one place and another piece is one piece. It should not be like this. That is what is called as continuous allocation. So whatever the amount of memory which is going to be required to run your process, that memory should be in continuous portion in one section of the memory. So we have 2 methods for doing this. First one, for continuous allocation practical implementation, we have 2 methods. Number 1 is single partition allocation. Number 2 is multiple partition allocation. So coming to the first one, single partition allocation, which is already done. You already know that whenever a CPU want to execute any particular process, first of all, it generates a logical address. The logical address must be always less than your limit value. The logical address is always, you may call it as offset address, you may call it as a relocatable, that is relative address, logical address, or may call it as a relative address, logical address, or may call it as relative address. Okay, this address must be less than your limit register. And in order to get the physical address, the content of base register plus offset is going to be added to get the physical address. In case whatever the address which has been generated, which is not less than your limit value trap, you're accessing that one. That's why already I told that in earlier. The memory protection is going to be done by using base comma limit register, or may call it as relocation and limit register. The memory management unit is responsible for converting logical address into physical address. The memory management techniques or memory management unit is a small program which is responsible for converting a relocatable, or may call it as a relative address into physical address, a logical address into physical address. So whatever the address you have been generated, the CPU generates always a logical address which should be less than your limit value, and it should be content of relocation register plus logical address is going to be added together to get the physical address. Simply I can call it as physical address is equal to content of base register or relocation register plus offset, or you may call it as a logical address, or you may call it as relative address. Now coming to this one, multiple partition allocation. What is this multiple? Multiple partition allocation in the sense you can allow multiple jobs at the same time in memory. You can have multiple jobs are going to be resident in main memory at the same time for execution. Okay. So now coming to the first one. So what is multiple partition? Now already I told that. Okay. In lower part of the memory, your operating system is running. Okay, lower part of the memory is running with operating system. This is user area for running your processes. This is upper part of the memory. Okay, now we'll see before going to the detailed discussion about the problem. Okay, so first of all, let us we'll see some of the important. The degree of multi-programming limited by number of partitions. So whatever the number of partitions which is available in your memory, so depending on that, if the number of jobs are going to be decided. Suppose you have 4 partitions are available, so that you can eligible for running maximum 4 processes. Okay, and you cannot do multiple jobs at the same time. Okay, in case if the memory is sufficient for accommodating more number of jobs, you can do it. Variable partition sizes for efficiently. Okay, size it to a given process needs. Now, I can use a word call it as whole, a block of memory which is available. Okay, the memory may be scattered not only in single area, various holes are there. Suppose in this area, okay, one process is running, and in this area is free, another process is running here, and the last one. There are 2 holes. So I can call it as holes in the sense a block of memory which is available. Whenever a process has been arrived, it is the responsibility of the memory management whether we need to load this particular process or not. Okay, first of all, you have to decide that which process has to be loaded. Once you decided to load, whether you need to check whether the whole whatever it is available which is sufficient for running this particular process or not. Okay, that's why we have been seen in operating system structures. Okay, the main duty of our operating system in connection with process management, keep track of which parts of the memory is full and which parts of the memory is empty, and keep track of which parts of the which process has to be loaded into memory and which process has to be not loaded into memory. So first of all, which process has to be loaded into memory, you need to decide. So once you decided to load, and you need to check that whatever the memory holds which is available but is satisfied for running this particular process. And next very important process, once the process execution is successfully completed, you need to remove the process from the memory. Yes, and after removing that, whatever the hole which is available, okay, in case the procedure are followed, any holes are there, you need to join them as a single partition. That is, partitions are combined. The partitions are combined. Okay, so and that implies your operating system must be keep track of which parts of the memory is already allocated and which parts of the memory is already free. Okay, so that's it. Let us take, okay, this all concept is going to be demonstrated by using one example problem. Now I have been, so when this particular process is going to be suffers from external fragmentation, when it is going to be suffers from internal fragmentation, they ask you the questions like this, then you need to write. The total amount of memory which is available in my computer system is 2560 kilobytes. The total amount of memory which is available in my computer system is 2560 KB. Okay, operating system consumes 400 KB. Operating system consumes 400 KB. For in order to run the user program, we required 2560 minus 400 be available with 2160 KB of free space available for running the processes. Okay, now there is 5 jobs are ready for executing in. Okay, ready for execution. Already I told you that the set of all jobs which are reside in secondary storage device those who are willing to come into memory, which is called it as job queue. That whatever the set of jobs which is already there, is all 5 jobs is not going to be copied into memory. So, okay, job queue in a sense, the set of all jobs which are reside in secondary storage, they are willing to come into memory. But the memory is not sufficient. Only some of the jobs are going to be selected from this particular secondary storage. The set of all jobs which are reside on secondary storage device is going to be called it as job queue. Those jobs which are willing to come into memory is called it as job queue. So among these particular 5 jobs, only some jobs is selected by job scheduler and copied into main memory. Then it is called it as ready queue. Ready queue in the sense, the set of all jobs which are waiting in main memory for ready for execution. They are waiting for CPU. Okay. Then your CPU is not having a capability of executing all jobs at the same time. Your CPU is having a capability of executing only one job at a time, so that which job is going to be executed by the CPU is going to be decided by process scheduler. That is the discussion. Now we'll see how it is going to be. Now, in order to complete process P1, it requires 600 KB of memory. The total time required to execute the process is 10 milliseconds, 10 milliseconds, and process P2 requires 1000 KB of memory. In order to execute such kind of process, it requires only 5 milliseconds. Process P3 requires 300 KB of memory, and it requires 20 milliseconds. Already you know that, okay, we cannot estimate the speed of an execution depending on the size of the program. The speed of an execution depends on time complexity, that is control structures and loops what we have been written inside. That's why. So that in order to execute 300 KB, it requires 20 milliseconds. In order to execute 1000 KB, it requires 5 KB. So it shows that the speed of an execution of a particular program does not depend on the size of the program. And in order to complete process P4, it requires 700 KB of memory. It requires only 8 milliseconds. In order to complete process P5, it requires 500 KB of memory. That is, it requires 15 milliseconds. How do you allocate the jobs? So according to this, first of all, we'll take one. So process P1. Now we'll see this particular one. This is my main memory. Operating system is running in an area 0 to 400. Now process P1 requires how much memory? 600. Okay, process P1 requires 600. So that 400 plus 600. So that is 401 to 600. It is occupied by process P1. And process P2 requires 1000 KB. From 1001 to 2000, process P2 is running. And process P3 requires only 300 KB. And process P3 requires only 300 KB. That is from 2001 to 2300, process P3 is running. Now we have been left with how much space? Another 260 is available from 2301 to 2560. 260 KB is available, but this particular 260 KB is not sufficient for running either P4 or P5. So P4 requires 500 KB and P5 requires 500 KB. This is P4 requires 700 and P5 requires 500 KB, which is not sufficient. So that's why this 260 KB is simply left out. This is called it as internal fragmentation. What is internal fragmentation? It is the smallest memory hole which cannot be accommodated for running any one of the waiting process. Which cannot be accommodated for running any one of the waiting process. Have you understood? Okay. So process P1 requires 600, process P2 requires 1000, and process P3 requires 300. So all three are allocated in a single segment. If this is one single segment, it is one single segment. P3 has one single segment, that is continuous allocation. So whatever the amount of space which is going to be required to run your process, that is allocated in one particular segment. The total amount of memory space is available is, okay, the total amount of memory space available is 260. The 260 cannot be sufficient for running P4 or P5. Why? Because P4 requires 700 and P5 requires 500. So it is the smallest memory hole which cannot be accommodated for running any one of the waiting process. Which cannot be accommodated for running any one of the waiting process. Hence, this kind of a concept is going to be called it as this kind of a process is going to be called it as internal fragmentation. So what is internal fragmentation? It is the smallest memory hole which cannot be accommodated for running any one of the waiting process. It is the smallest memory hole which cannot be accommodated for running any one of the waiting process, which is going to be called as internal fragmentation. Okay, among P1, P2, P3, okay, P2 is successfully completed after 5 milliseconds. Okay, then in that is what happens is that so process P2 has been terminated. So you have a whole of 1000 KB here. You have another whole of 260 KB here. You are having two memory holes. One hole accommodates 1000 KB. Another hole holds 260. Now what happens is that process P4 is entered into that place. From 1001 to 1700, it is occupied by process P4. Now you have another 300 hole is empty here. Another 260 is empty here. Now we have two holes. This hole, this memory space here, this is a 300 memory space and this is 260. Total together you have 560 is available. So this 560 is sufficient for running P5. Why? Because P5 requires only 500 KB. Okay, 800. So when the external fragmentation is going to be, now external fragmentation occur. Now what is this? The total amount of memory available is 560, but you cannot run the process P5. According to continuous allocation, whatever the amount of memory which is going to be required to run your process, that memory should be in continuous fashion. But it is not in a continuous fashion. 300 here and 260 here, you cannot accommodate for P5. So after that P1 is completed, then P5 is going to be allowed here to run. Is it clear? That implies, what do you mean by external fragmentation? External fragmentation is simply defined as the required amount of memory is available, but it is not in a continuous. The required amount of memory is available, but it is not in a continuous fashion. Hence, the user cannot able to run the program. The required amount of memory is available, but it is not in a continuous fashion. Hence, the user cannot able to run the program. This kind of a concept is called as external fragmentation. So, internal fragmentation is arised in after and before entering into P4. External fragmentation is arrived in before entering into P5. This is the answers what you need to answer. So they simply ask you by bringing this question when external fragmentation is occurred and when internal fragmentation is occurred. So what is internal fragmentation? It is the smallest memory hole which cannot be accommodated for running any one of the waiting process. That is called as internal fragmentation. What is external fragmentation? External fragmentation is simply defined as, okay, the total amount of memory space is available, but it is not in a continuous fashion. Hence, the user cannot able to run the program. That is called as external fragmentation. Okay, like this. So that now there is a lot of, now we have here two memory holes empty. You have one memory hole like this. The total memory is going to be divided into holes. Now, whenever a new process has been entered into your computer system, how do you allocate it? Now, before going to this particular thing, first of all, we'll see how do you do this particular process. Suppose if in case you want to execute process P5 in this situation, we use a technique called it as compaction. So what is compaction, or we call it as relocation? If the process P3 is moved towards up, then we have 560 as a single hole so that we can run. This process is going to be called as compaction. Moving your processes either towards up or down, making as a single memory hole empty, which can be accommodated for running your processes. That is called as compaction. So compaction is a process of moving your processes either towards up or down for making single memory hole empty is going to be called as compaction techniques. Okay. Now, this is what is compaction. Okay. Or I call it as a relocation. Now, coming to the next very important one is whenever a new process has been arrived, whenever a new process has been arrived, how to allocate a hole for them? To allocate a hole for them, there is multiple holes are there in your computer system. How can you allocate the holes for them? The allocation is going to be done by using three types of algorithms. That is first fit, best fit, worst fit. What do you mean by first fit? So allocate, what is first fit? So you please try to sequentially search in the memory holes wherever you have been found as sufficient for running your process. Please try to fit them and run it. Such kind of an algorithm is going to be called as first fit. That is, allocate the first hole that is big enough. Allocate the first hole big enough for running your process. Please try to allocate in the area. Searching can be started either at the beginning of the set of holes, wherever the holes, or otherwise where the previous first search is ended. You can implement it as your wish. There is no problem. That's always depending on your operating system designer. So we can stop searching as soon as we'll find a free hole that is large enough to run your process. That is first fit. Number two, best fit. Allocate the smallest memory hole which big enough. That implies allocate the smallest memory hole which causes a less internal fragmentation. That is going to be called as best fit. Allocate the smallest memory hole that big enough must be. Okay. The entire list. You have to search in the entire list, and which hole is going to be causes you the less internal fragmentation. Please try to allocate such kind of. That is best fit. Okay, and coming to the third very important one is worst fit. Allocate the largest memory hole. Must also search in the entire list. You need to search in the entire list and you need to allocate the largest memory hole which is required to run in this particular process. Okay, that is which causes a lot of external fragmentation. And please don't try to think that okay, best fit is always best fit and first fit is always best fit and worst fit is always worst. Don't think like this. In some situation, the worst fit is the best fit. In some situations, the worst fit is the best fit. In some situations, best fit may be worst fit. In some situations, worst fit may be the best one. In case if the program is, while program running, the memory requirements is static, then best fit is the best algorithm for implementing such kind of a thing. If the memory requirements for the process is dynamic, that implies the memory requirements is going to be decided at the time of execution, then best fit may not be okay the best. In that situations, at that time worst fit is the best. Why? Because at the time of execution, the memory requirements may be changes. Yes or no? So we are allocating the largest memory hole so that what happens is that whatever the amount of memory which is going to be required, it is going to be continuously available so that it will worst fit is the best fit in that dynamic situations. So that's why depending on static and dynamic requirements, we are deciding that which one is the best and which one is the worst. Okay, now first fit and best fit better than worst fit in terms of speed and storage utilization. In terms of speed and storage utilization. But in case of a dynamic storage, the worst fit is the best fit. Okay. Now, so coming to the conclusion of this particular topic. Okay, conclusion of this particular topic is that okay, now we have been defined external fragmentation, internal. What is internal fragmentation? It is the smallest memory hole, which is the smallest memory hole, which cannot be accommodated for running any one of the waiting process is going to be called as internal fragmentation. It is the smallest memory hole which cannot be accommodated for running any one of the waiting process is going to be called as internal fragmentation. Number two, external fragmentation. The required amount of memory is available, but it is not in a continuous fashion, hence the user cannot able to run the process. Hence it is called as external fragmentation. In order to overcome this particular one, we use a compaction techniques. Already I told you that compaction is nothing but moving your memory segments either towards up or down, making as a single memory hole empty. That's this is completes our discussion. So today, what we have been seeing at a glance, we'll see what is a memory. A memory is a large array of words or bytes. Each and every one is having its own address, and CPU will going to be simply fetching the instructions according to the value of the program counter. And after that, we have been seen about what is absolute address and what is relative address, and followed by we have been seen that okay, address binding concept. What is this address binding in the sense? So at the time of compilation, your process may get one type of addresses, that is completely absolute addresses. At the time of execution, at the time of loading, at the time of loading and execution, you are going to be getting different types of addresses is going to be called it as, that is load time address and execution time addresses. All are not same. And after that, we have been seen about okay, logical address and physical address. The CPUs always generates a logical address. It should be less than your limit value, and it should be added with content of base register or relocation register to get the physical address. That is what we have been seeing. And after that, we have been seen about continuous allocation. What is continuous allocation in the sense? Okay, whatever the amount of memory which is going to be required to run your process, that entire memory should be allocated in as one segment. That is called as one. Okay, continuous allocation. We haven't seen about single partition allocation, multiple partition allocation. So we have been arrived at the two terms, internal fragmentation and external fragmentation. We have been done. And so the different kinds of algorithms which is required to allocate a whole for a particular process is either first fit, best fit, and worst fit. This is what we have been seeing today. These all techniques we have been seeing today is if the memory is sufficient for running your processes. The next topic of discussion is that whatever the amount of memory which is going to be required to run your process, it's not sufficient for running. It's not sufficient for running your processes. Then how can you run? You can run such kind of a process by using virtual memory concept. You can run such kind of a process by using virtual memory. That is the discussion of the next topic, virtual memory. Okay, already we have been defined what is virtual memory. Virtual memory is a concept which gives an illusion to the programmer that he has a large amount of memory, relatively having a small amount of memory. Such kind of a memory management techniques we're going to see in the next class. Is it clear? So this is discussion about for today's class. So today we'll see virtual memory. Tomorrow we're going to see that virtual memory and virtual memory techniques and problems on virtual memory. We'll see. This is a complete discussion about today, and we'll see in the next class. So now I'm stopping my presenting. Is anybody is there for assisting this? Can I stop presentation now? Yes, 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 sir.